we've been talking about in the last few lectures is the general theory of entanglement, right? And we learned a few different of the foundational points associated with that. What I want to talk about today, and we'll talk about for the next few lectures, is the realization of entanglement in quantum optics. And in particular, what I'm interested in discussing is entanglement in the quantized electromagnetic field. Now, this is actually quite an involved subject. It's not as straightforward as you might initially imagine, because as we discussed last lecture in their little makeup yesterday, entanglement is kind of in the eye of the beholder to some degree. It really depends on what are the subsystems that you're looking at, and how are you dividing, what are the degrees of freedom that you're actually trying to measure. Okay? So there are different ways we can think about the electromagnetic field, different kinds of degrees of freedom that we might think about entangling. The sort of most straightforward thing that you might think about is think about two photons. And we might talk about polarization in entanglement. So there we have, those are our degrees of freedom are associated with the spins of the photons, their polarization. And that's a pretty straightforward kind of thing that we know how to describe quite well. We have our Hilbert space associated with those degrees of freedom. They're kind of isomorphic to two spin 1/2 particles when we write our Hilbert space in terms of that kind of tensor product. And we might say, well, okay, we have some kind of standard basis to describe this particular Hilbert space associated with two photons. And traditionally, sort of my friend Paul Kwiat, and everyone uses this notation now when we talk about polarization, you got the horizontal and vertical as my two orthogonal states of polarization. Think about them as linear polarization, and this would be the standard basis for that space, right? And we would write a general state of these two photons in terms of some kind of arbitrary decomposition of this sort, where these now are representing the indices, whether it be H or V. And as we have discussed in recent lectures, the degree of entanglement is related to the Schmidt decomposition. So that's a pretty straightforward thing to think about, right? Now, another way we might think about, instead of thinking about the spin degrees of freedom of the photon, we can think about the orbital degrees, as you like, or the motional degrees of freedom of the photon, all right? So another thing we might think about is, we'll think about two photons, and we'll talk about what is often termed momentum entanglement. And, well, it's a slightly more complex description of the system. We would say, in that case, our Hilbert space of interest would be representing, now we have infinite dimensional Hilbert spaces. We might say they're the Hilbert spaces associated with square normalizable functions, maybe in three-dimensional space, if our photons can propagate in three-dimensional space. So if we have some state, say that is in one of these Hilbert spaces, it generally would be of the form let's see. Yeah, so this is for one of the photons. With some important amplitudes there, right? So this is the kind of the momentum space wave function of the photon, and we would say this is in that space if square normalizable. So an arbitrary state of the system, and here, of course, there might be some polarization index, but we're assuming in this case, if we're talking about the sort of motional degrees of freedom or the momentum degrees of freedom, we would say to take all the photons to be polarized in the same direction to start. And then an arbitrary state of the joint two-photon system in this Hilbert space would be of the form well, we have two photons, and there's some two-photon wave function. And that would describe the arbitrary two states here, or state with two photons in it, with arbitrary two-photon momentum. Now the question of entanglement here is trickier because we don't have an obvious way to think about a Schmidt decomposition of a matrix. In this case, these are infinite dimensional Hilbert spaces. But, I mean, we could do the kind of taste test on this and just see what the entropy is of the marginal state. That'll tell us something about the entanglement. And more formally, in fact, we can, and we'll look at this and homework, I expect, where we, even in the infinite dimensional case, we can write down this mu is a different mu, and then we'll just the typical index that we're using. So we can, even in the infinite dimensional case, write down a Schmidt decomposition. Generally would go to infinity, but maybe there's only a finite number of non-zero Schmidt coefficients in this decomposition, and that would say there's a finite amount of entanglement. So really I should say, used in the same way that we've done before, even though it's an infinite dimensional space, typically this would go up to some maximum index, and the Schmidt rank would tell me something about the entanglement in momentum, and the entropy of the Schmidt coefficients will tell me a quantitative measure. So we could do that, certainly. Okay, so those are fairly straightforward things. But let's consider the following, that may be a little less straightforward. Let's suppose we did the following brain dead thing. I take a photon, it's in some incoming mode. Let me just keep my notation straight here. I think it really matters, but okay. So let's call this mode A. And let's just say I put it on a beam splitter. Okay, so let's say I did this. This was a single photon. And there's a mode B, and there's a wave vector associated with that direction. There's a wave vector come out. Okay. Is that an entangled state? Well, sure doesn't look like it. I mean, this is is, you know, from elementary quantum mechanics, we would say I have a superposition of plane waves. It's a superposition state. But what the heck are you throwing entanglement at me? So that's nothing to do with entanglement. This is just a superposition. I mean, if I take an electron and, you know, you do the famous Davidson-Gerwer double slit experiment, you put an electron in a double slit, you go one way or the other. There's no entanglement. This is about superpositions, right? Well, yeah, but, so, you know, we would write this state typically, say, okay, this state in this goes to a state, and let's say this is a 50-50 beam splitter, and let's say that the phases were set such that you have a superposition with a positive sign in between. Okay, so entanglement, I don't think so. However, we can look at this in a slightly different way. Let's suppose, I'll come back to the front board here. So let's suppose that I look at this in second quantized notation. Okay? And so we know, as we've discussed and studied before, I can think about this classical beam splitter transformation. Yeah?
So before the beam splitter, you have Ka, and after the beam splitter, you have Ka again.
That's right. You have some fraction that gets transmitted, and some fraction gets reflected. And if it gets transmitted, it's in the same wave vector. So it's one photon. There's some probability, if I can think about this, you know, I put a detector here, or I put a detector here, there's some, I mean, this is a, you know, if you wanted to go back to the first quantized notation, this is one photon in the state, in the mode Ka, and this is one photon in the mode Kb. But the reason I didn't write it this way is, this is quantum mechanics that you've learned. It just, you know, I want to make it more complicated. I say there's an electron, it's in a plane wave state. It's in an eigenstate of momentum. And then afterwards, it's in a superposition of two momentum eigenstates, right? Now, I could, and I will right now, say, let's look at this in second quantized notation. And in particular, what we have studied is that the scattering type of transformation that happens on classical waves, which that's what it is, that's a scattering transformation, can be thought of or treated quantum mechanically for quantized waves in terms of a transformation on the creation annihilation operators. So, you know, generically, you know, if I have some, say, annihilation operator for this mode, there's the creation for the in wave, or annihilation for the in wave, and the similar one for mode B, and then we have the out. So the scattering matrix that you learn about in your advanced quantum course tells you how to go from the incoming waves to the outgoing waves, right? That's the S matrix. So if this is a linear beam splitter, this is a linear transformation. So for example, this is equal, if 1 over root 2, it's a 50-50 beam splitter. And we can have this be this. Okay? Could have eyes in there. It sort of depends, is it a symmetric beam splitter or not? But that's a 50-50 beam splitter. Okay? So we know that from our study. So let's suppose that, so now I'm going to say I'm going to take into account these two modes. Okay? So my in state is I have one photon in the mode A. So I'm going to create one photon in that mode. Of course, there's the vacuum in A and the vacuum in B. That's the shorthand when we write 0. Okay? And now my out state is the scattering operator acting. All right, so this I would call 1A, 0B. Okay. Now, my out state is the scattering operator acting on. That's what the scattering operator does. It takes in to out. And this is really shorthand for S, A, S stagger. And similarly for the B. So I do that transformation, and I get 1 over root 2 A in plus B in dagger acting on the vacuum, which is 1 over root 2 1 A 0 B plus 0 A 1 B. Well, that kind of looks like an entangled state. I mean, it's got a superposition of bipartite things into different states, and it looks entangled. I mean, it's the same physics. I just wrote it in a kind of more complicated way. Now, this caused a lot of confusion. I don't know, maybe a decade or so ago, about should I really call this entangled state or not? Is this in any way entangled? Well, yeah, it is. I mean, this is, and I'm trying to convince you why this might make sense. This is what we call mode entanglement. It's not a lot of entanglement, but it's a mode entangled. The question is, what are the degrees of freedom that I'm talking about? When we're talking about the quantized field, there are different kinds of degrees of freedom I can consider. I can consider particles, or I can consider waves. What I described at the beginning of this lecture was particle entanglement. Entanglement where I thought about my degrees of freedom as the particles. And if I only had one particle, well, then I don't have any entanglement. But if I think about the waves, the continuous variables, well, then a beam splitter is an entangling operation. It's a little weird to think about it because it's linear optics. And we usually think about, in order to do entangling, that's hard. But sort of depends what we're trying to do, as we'll see through the course of this lecture and next week. Because as we discussed, an entangling Hamiltonian is not separable. But separable in what? Separable in the degrees of freedom that are being considered. So what is the Hamiltonian that generates the scattering interaction? Well, it's an interaction that, say, annihilates a photon from one mode and creates it in another mode, right? So the Hamiltonian would be of the form, in this case, there's some constant. And what I do is I annihilate a photon in the A mode, created in the B mode and vice versa. And relative to this description of the two modes as my, so in this case, my Hilbert space looks like this, where each one of these is an infinite dimensional Hilbert space of a harmonic oscillator. It represents the mode. It's a tensor product space. I can have entanglement. And this is a non-separable interaction. Now you might say, all right, fine. Yeah, there's some math there, but come on. That's not entanglement. I mean, all you did is you did that. You made a superposition of two plane wave states. But in a sense, it is a resource if we want to think about it. Let's suppose I do the following Gedanken experiment. Let's say that what I'm going to do is I'm going to put it, so I have this single photon wave packet that comes in. It's in the mode A. Okay? And now I send it in, I have a superposition of the two wave packets. I mean, it's really a long, long wave packet if it's Ka, but let's give it some finite. It's called the modes, not plane waves, but big wave packets. Okay? And now what I'm going to do is I'm going to call up my buddy, Nobel Prize winner Serge Roche. But anyway, pretend, and he has these superconducting cavities with atoms in them. Okay? And I can put one on each side of the output port of this beam splitter, this 50-50 beam splitter. Okay? And I'm going to prepare the atom in the ground state in both of these guys. All right? And we know that if the cavity coupling constant is set up just right, and if the duration of the interaction is just right, then when that cavity goes through, when the photon goes through the cavity, we can have an interaction where if I have one photon in the mode and the atom in the ground state, then there is a unitary transformation that happens on the atom which does this kind of Rabi oscillation where the photon goes into the excited state. Okay? So we can do that. We can set up the cavity to do that. So let's think about what happens. What's the description? Now I have I have two other degrees of freedom, two atoms. So I have this multipartite description. So my total state of the system initially, say, is one photon in mode A, nothing in mode B. I have atom 1 and atom 2, both in the ground state. Okay? Now I go through the beam splitter, and well, this state becomes this state. Right? So this becomes 1 over root 2 I'll call this GA and GB. This is the atom at output port here, and this is the atom at output port there. Okay? So, I'll rewrite this a little bit. As follows. Have 1 GA 0 GB, okay, plus 0 GA tensor 1 GB B. Of course, this transformation is such that it does not, if the atom is in zero, I mean, if the photon is zero, nothing happens.
I think you want to switch your labels in your picture, your ground state labels. Something comes out of mode A and it's in ground state B.
Let's see.
Because you mean A for horizontal, right? So for the cavity.
Oh, here.
Yeah.
This is A, and this is B. Yes, thank you. Pardon me. Thank you. Thanks, yeah. Okay, so now, after the photon, now it's just passing the beam splitter, now it passes to the cavity. Now you see what happens. This guy goes to the excited state, and the photon is gone. And in this guy, you got 0 eV. So what do we got? What we have in this case is now the photons are both in the vacuum, but I have this state. For my two atoms. You would grant me that's an entangled state, right? Sure looks entangled. So this is a resource for generating entanglement. What we've done here is entanglement swapping. We've swapped the entanglement that was in the modes and swapped it out with the atoms. So it is a kind of entanglement. And it can be used as a resource for doing teleportation, as we will see. Yeah?
Are there any interesting things that we could get out of putting coherent states in there? Because if that were the case, I mean, it seems like that would really be like too powerful.
The answer is no.
Okay.
So that is indeed very important. As we know, so let's think about that. It's a good question. So it was important that this was a single photon state.
Yeah.
If this were a classical wave, then it really does seem like there's something weird, really super weird going on. So suppose that the state that went into this wave packet, or I'm sorry, that went onto the beam splitter was now coherent state in mode A, and the vacuum in mode B, okay, as opposed to the state 1, 0. Well, we know how to write, so that's my psi in. Which we can write as the displacement operator acting on the vacuum, right? As we know. So, I think we did this one for homework, and we all remember it very well. What happens when I send this scattering operator on this? What do you get? You get a product state. In fact, what you get is equal to the displacement on mode A, 1 over the square root of alpha, square root of alpha. And this is equal to the product state with half the intensity transmitted and half of the intensity reflected. It must be. So it is indeed true that in order to make entanglement, we need, through this kind of entangling interaction, it's not universally entangling on all input states. The amount of entanglement that you generate depends on the negativity of the P function. So as long as you have something that's not a coherent state or a statistical mixture of coherent states, you will generate entanglement in this sense, mode entanglement. Not particle entanglement, but mode entanglement. So that's where the connection between negativity of quasi-probability distributions can be thought about as a resource for quantum information processing. So in particular, what we'll talk about maybe this lecture, maybe next, is what happens when you put squeeze states through there. Now, squeeze states, as we described, they have positive Wigner functions. So in some sense, they're classical. But they're not really classical in the sense of the P function. In fact, if you put a squeeze state on, what comes out here is entanglement between the two modes. And that's what's used, for example, in continuous variable quantum teleportation. That's something we'll talk about. All right, very good. Okay, so with that said, I guess there's one other thing I did want to say about this thing. Another way we can look at this that connects to what we discussed last lecture is another way that we can see that this is an entangling interaction on the continuous variable degrees of freedom rather than the discrete variable degrees of freedom is consider the transformation on the quadratures. So my quadratures for K and D, they're defined in terms of position and momentum like operators in terms of these harmonic oscillators. Right? So now the question is, what is the scattering interaction, which we just erased, due to the quadratures? Well, it does the following. XA, XB, or let me write it out this way. Easy, a little bit of algebra can be to the following. Using the same thing that we said about the equation annihilation operators. This is equal to XA plus XB over root 2. Look familiar? Indeed, we talked about the transformation of coordinates on a particle, that if I went, say I have an electron and a proton and a hydrogen atom, they're entangled in relative coordinate and center of mass, but they're entangled in electron and proton, but they're separable in the center of mass and relative coordinate. And making a transformation from local coordinates to center of mass and relative coordinates is an entangling interaction. And that's what we're doing. This kind of transformation is entangling A and B by changing the coordinate system. That's all we're doing, really. But of course, these are not the particle's position and momentum. This is a very abstract position and momentum. These are the quadratures. Yeah, I mean, there's just too many X's and P's floating around. It can drive you crazy. But this X is not the position of the momentum. This X is the quadrature X associated with the oscillator of the wave. So that's why this is an entangling interaction. All right. Coolio. All right, let's continue. So now what I want to talk about is the physics a little bit more. How do we actually, how does one, I mean, we say, okay, we can make entanglement with a beam splitter if we have non-classical light to start, but we need that. So we need, at least even though the beam splitter is a linear optics kind of thing, if we're going to make entanglement, we've got to think about nonlinear optics. Because it's only through nonlinear optics that we can make things beyond coherent states. So what we want to talk about is the particular nonlinear optics, the kind of workhorse of entanglement. Parametric bound conversion. So we discussed this when we were talking about the generation of squeezing earlier in the semester. And we talked about this in the context, firstly, of classical nonlinear optics, where we, for example, had parametric amplification. So in parametric amplification, what we considered was the following situation. We had this Chi2 crystal, and these are fancy colors. So we have our, oh boy, this is gotten dark. Doesn't even look like color. So I don't want to, it's too spread. Never mind. We'll show pictures. I'll come back to this afterwards. So let's just write this. At the pump, at some frequency and some wave vector, which is we typically call the z direction. And if we inject into this crystal another beam, which we call the signal that we want to amplify, which has some much lower frequency than omega pump, then there is a process by which we can transfer energy from this beam into this and amplify it. Okay, that's parametric amplification. And of course, it's a three-wave mixing process, so what happens is we also generate another beam, which we call, so this is the signal, and the vestige of radio jargon, this is called the idler. So we end up having that kind of process whereby we amplify this beam and simultaneously we generate a new beam such that momentum and energy are conserved inside the crystal. So the sum of the frequencies add to the pump frequency, and the total momentum is conserved. The sum of the wave vectors of the signal and either inside the crystal have to add to the pump. And that, as we discussed, is called phase matching. Now, we also know that even if I don't inject a particular signal into this crystal, we can have the spontaneous generation of these two photons, just because, I should erase that one. Let me keep that. So I'm going to try to draw some colors on here. So I might have, for example, a pump come in, and I have some red and yellow photons come out that satisfy the phase matching condition. However, if I don't have the signal here, then this is a spontaneous process. It's a spontaneous decay, or emission, if you like, of these two photons. It's involving an annihilation of this ultraviolet photon conjoined with the creation of this pair of photons, the photon pair, the signal, and the atom. However, there's nothing that particularly picks out these two photons with those particular wave vectors. We could, in principle, have another process that comes in, where we have the same pump, but now we have a different phase matching condition that's satisfied. There we have another good color. A darker red. Right, so we have a darker red. So there are a whole collection of possible pairs of photons, of signal and either photons, which can add such that their frequencies add to the pump and their momenta add to the pump. And since these processes are not, they're in principle indistinguishable, meaning there's no information that's stored in any other degree of freedom that tells me which of these processes and the uncountably infinite number of possible choices that happen, then I have to, according to Feynman's rule, add the probability amplitude for all of the possible choices of two photon or photon pairs that are generated from the pump photon. And the result is a two-photon entangled state. So this is the workhorse. All the first really cool experiments on looking at Bell's inequalities and two-photon interference, it all really took off in the late 80s and early 1990s when this kind of nonlinear optical process was really perfected and looked at carefully in terms of its quantum properties. So what I want to talk about then is what are the types of entanglement that are produced by this? Yeah.
So I guess just before you start that,
Yep.
so what limitations are there to using the type of mode entanglement that we were just talking about before to do those sorts of experiments?
Okay, so I think I'm going to wait a little bit on that, but it depends what I want to do, okay? If I want to, for example, test a violation of Bell's inequality, I have to think about, and we'll talk about, that's why I want to wait a little, we're going to talk about that next lecture. What does it mean to talk about Bell's inequality for X and P? It's kind of a hard thing to think about, and people sort of struggle with that. In fact, the fact that the kind of mode entanglement that we can typically make, which is based on entangling squeezed modes, and because the Wigner function is everywhere positive, there is a local hidden variable theory that describes it. It's called, the local hidden variable is the Wigner function. So we're going to talk about that next time, but that's, whereas if we're talking about discrete variables, we can do a CHSH Bell inequality, which we'll review next time, and then, yeah. So in some sense, it's much more powerful. But it's not everything, and we'll talk about, yeah, so we'll build those layers as we go. Okay, so let's talk about this kind of process, and let's talk about the kind of entanglement that is produced. So in order to satisfy these conditions, you'll remember these phase matching conditions. Remember that K here, the magnitude of K for, say, the pump, is omega over c times the index of refraction of whatever that pump wave is at that frequency. And similarly for the signal in Eibler. So that because of the fact that this problem is dispersive, we have to be quite careful about how we choose those indices of fraction. Otherwise, there's no way to satisfy both this and this except along one direction, right? So, and this sort of gets a little bit into the weeds, and there's only so far into the weeds I'm willing to go. But it's important to have, to understand a little bit of the optics, the real optics here, the optics in quantum optics, if we're going to understand what the heck is being produced, what kind of entangled state is being produced in the system. So in particular, as we discussed a little bit when we just introduced this notion of three-way mixing, there's kind of two ways that one thinks about phase matching this kind of three-way mixing. There's what's called type 1 and type 2. So let's talk about type 1 phase matching. So in type 1 phase matching, what one does is choose this condition, or these two conditions, to be satisfied such that these, the down-converted photons, they're called down-converted because they have less frequency and less energy than the incoming, have the same polarization, but that one is orthogonal to the pump. So one chooses the pump index of refraction to be the so-called extraordinary index. And we choose the signal in Eibler to have same dispersive nature, but for the so-called ordinary. Now the term ordinary and extraordinary, you know, that kind of about birefringes and blah, 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 it doesn't really matter. They're just names, that's all we care. The point is that you put in a pump that, say, is that's polarized in the extraordinary direction relative to the optic axis of the crystal, and you get out down-converted photons that are polarized perpendicular. And those two, that's called the, so this kind of configuration is called type 1 phase match. Now, and this was the workhorse at the beginning. All the first experiments were done this way. And let me explain what kind of entangled state comes out of such a system. Well, firstly, there's no polarization entanglement here because they have the same polarization. So we're not talking about polarization entanglement if we're talking about a single crystal and type 1 phase matching. So what are we talking about? Well, we're talking about a kind of momentum entanglement. So, it turns out that if you try to satisfy these two, so what do I have? So for type 1 phase matching, my conditions can be written as follows. Omega P is equal to omega S plus omega I, and then I'm going to call this angle relative to this theta of that angle of the spontaneously emitted photon for the signal theta S and for the idler theta I. So we have that omega pump over C times the extraordinary index function at that frequency cosine, no, it's all in that direction. And then we have omega signal over C and ordinary at the signal cosine omega, phi signal theta plus the ordinary index at the idler cosine idler. And then I have the transverse component. Okay, so that's just looking at these phase matching conditions and breaking them up into the component along the pump and the component transverse to the pump. They're all in the same plane, or at least there is a plane in which, yeah, this particular pair are all in the same plane. So now you have to just solve this set of equations. You have to know something about all this stuff. There's just a little bit of geometry to do it. We won't do the details here, but here's what happens. So attempt to draw just a little bit of, here's the crystal, okay? And now we have our pump. Comes in. And in here, there's somewhere down the line here, one of these parametric emissions happens. And we don't know which one's going to happen, but if a photon of this color happens, it's emitted on a cone. Okay? And if a photon is of this color, it's emitted on a cone with a slightly different angle. And if a photon of this color is in this angle, etc. Whether the red's outside or the green is outside, it depends on, is it a negative axis, blah, 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 higher frequency, I don't know. But it, you can, yeah. Okay, fine. All these colors are emitted. However, let's look at this head on. So if I look at this on this face, there's the red, all the red photons are emitted on that cone. That. Like that, okay? Now, what has to happen here is the following. Which we have to satisfy the phase matching condition, which means that, for example, if a red photon is created, then it must have a twin which has green eyes. And because of the phase matching, it has to be over here. Or maybe the photon was emitted over here, to make it this guy, in which case, you know, sister is over here. I might have chosen it such that, oh God, so happily it doesn't look like this and all your circles are non-concentric, but get the point, I hope. And of course, it might be that this is the degenerate case, where this is half the pump, right? So then, you know, every time a yellow photon is over here, you know, a yellow photon is here. Or maybe a yellow photon is here, and then a yellow photon is there. So let's give it the purple horseshoes. Green clovers. So the point here is that these represent all possible processes that can happen. And of course, there's an infinite continuum, uncountably infinite number of possible choices that can happen in this case. All right? So how would I describe the state of this system? So the Hamiltonian that we discussed for three-wave mixing looks like the following. Well, so we have some constant that is, you know, depends on pi2, it depends on the intensity of the pump in the non-depleted pump limit, where we treat the pump as a classical field. And then there's all the possible signal in either. And we'll take this to be perfect phase matching conditions. Of course, this depends on there being an infinitely long crystal and a perfect plane wave and a perfect monochromatic continuous wave pump, but, you know, just to get the idea. So they're both ordinarily polarized, they have two photons, and they, oops, that's the Hamiltonian, plus the conjugate.
You need an annihilation operator there, right?
I don't, because I've treated the pump classically. So the full Hamiltonian would indeed be annihilate the pump in the pump field, and it's a three-wave mixing. But when we, as we said, you know, when we do the model transformation and we make the non-depleted pump approximation, we treat the pump as a classical field, and that is buried in that coupling constant. So there's also the inverse process whereby I could in principle up-convert, but it's just smaller. Okay? But it's there. Now, the state that I get after I integrate for, or evolve for a time, the length of the crystal over the speed of light acting on the vacuum. If this is a weak interaction, which it generally is, this K is pretty small, we'd love it to be bigger, but it just isn't, means that, you know, to lowest order, this is zero, some zero photon state plus some 2 photon state, and then there's some K squared, 4 photons, blah, blah, blah. And this is just small. So if we just look for the part where the 2 photon sector of this, it looks like the following. Well, I'm going to be mean and just do this. Okay. With some normalized in some sense. So the state that is produced by this parametric down conversion process is what we called at the beginning of lecture momentum entangled. And it's a pretty complicated entangled state because it involves this continuum of possible terms, all as long as they satisfy the phase matching conditions in this idealization of the problem. Now, typically, one talks about this kind of state, and a lot of the initial experiments that were done in studies of this kind of separated the problem in 2. There's something that has to do with the direction of propagation, and there's something that has to do with the color of the light. And if I think about the color of the light, the frequency, that's related in some sense to the arrival time. There's a kind of time energy, and then there's momentum. So typically what is done in these experiments, for example, is to look at this kind of output from here, not look at all the photons, but just look at some subset of the photons that I can pick out with some apertures or pinholes. I could do that, for example, I could put, say, a pinhole here and here, and collect these 2 photons. They're entangled. Or I might collect this photon and that photon. They're entangled too. And when I do that, I'm basically, the pinhole can have a very small pinhole that basically defines a direction. Of course, it's not that small, and so there's still some spread in colors here. Although I did do it yellow, there's yellow to green, a little bit more to the orange in between there. So when one picks out, puts in these pinholes, one defines a kind of spectrum of the photon. It's defined in this case by whatever, because of the correlation between color and cone angle, this is a kind of filter function on the photons. So once I do that, one often will see this kind of state written as following. It's approximately equal to the following. Where this function is determined by the spectrum that I described over there, by whatever that aperture function is, or maybe I put some kind of other neutral density filter thingamajig up in front of it that filters out some extraneous filter. So what does this kind of state look like? So this is an entangled state. Sometimes we call this energy entangled. This is a jargon that people use in the field. Typically, they talk about momentum entangled when they're talking about the transverse direction rather than the longitudinal direction. And what this says is, well, the two photons are created with this correlation in frequency, assuming perfect phase matching, such that one photon has this frequency, we call it the signal, and the other has the conjugate frequency, which should have been that. That equals omega I. But what the signal frequency is there's some coherent distribution of possible signal frequencies that are defined by this aperture. Now, one of the things that's interesting is suppose we did the Fourier transform of these into the time domain. So I can think about an arrival time of the photon. Then what this would look like is the following. It's a kind of time energy uncertainty. What does this state mean? Well, what this is saying is that if I put my detectors, out here, and I were able to resolve when one photon arrived, then what this is saying is that this function is such that I don't know when the photon is going to arrive, but what I know is that the time separation between the two photons, let me call them signal and idler to be clearer, is defined by this function. And this function is just a Fourier transform of that function. So the degree to which this is broadband, this can approach a delta function. Which is to say the following. The two photons that are born in this crystal are born essentially at the same time. But I just don't know what their birthday is. Their birthday is just completely uncertain to the degree to which this is a continuous wave. It's not something that has finite bandwidth. It's just infinitely narrow omega p. And this crystal is infinitely long. Of course, none of that's exactly true, but, and of course we have finite bandwidth due to these apertures, but the time scale is typically, in typical experiments, this separation time is typically on the order of a nanosecond. Even though there's not a single pulse. This is not a pulse laser experiment. These are not nanosecond pulses. This is all CW, in the light jargon of lasers, continuous waves. It's all just, however, because of the quantum fluctuations of this thing, we have some kind of correlations in the problem. And this was what was done, as we discussed at the very, very first lecture last semester, in the Hongo-Mendel experiment. What was done in the Hongo-Mendel experiment was to take this kind of crystal, put these apertures here, define your signal and either photons, and then bounce them back onto a beam splitter, 50-50 beam splitter. And then have detectors and coincidence counts. And so these signal and Eiler photons are born, they're born in some sense in very, very narrow wave packets. We just don't know where the center of the wave packet is. And as we know, as we discussed, when the two photons hit the beam splitter, they always go off in the same direction. So the coincidence counts would be 0. And then you put a little bit of a delay line in here. And you look at the coincidence counts as a function of the delay line, and you find the following. When delta L is 0, you get no coincidence, and you get a dip. This is the famous Hahn-O-Mendel dip. Dip is the technical word. And the width of this dip is determined by this. Because the spectrum here determines the correlation time. All right, I want to just finish this lecture by talking about something else that's important on this. What about type 2 phase match? Let me just, I don't know if we'll be able to finish this, but let's get started. So in type 2, the signal in either have orthogonal polarizations. So one is ordinary and one is extraordinary. And you set up the crystal such that that is the case that's phase matched. Now you have to go through all that phase matching thingamaboozit again. But what happens in this problem is the following. Get a chalk. So now what happens is the signal and either photons are not born, they're born on cones, but not the same cone. So what happens is the following. Given that same pump, if I get a horizontal photon on that cone, then I get a vertical photon on that cone. Okay? So once again, they're born in these pairs such that if a photon is born here, then its twin is over here. And this one is vertically polarized. Okay? If you set things up properly. And if, so similarly, we can have that color vertical. Then we get, there's a conjugate one, I'm sorry, pardon me, horizontal. All these are the horizontal guys, and these guys are vertical. So I could get, you know, a guy over here, and its conjugate over here. So then I have an H and a B. Now the degenerate case is the most interesting. That's yellow. I didn't draw it so well. We'll get something off Google and we'll look at it on the screen next time. But here's the point. So these guys are horizontal, these guys are vertical. But there are these two very special points where I can't tell which cone it came from, right? If a photon is emitted here in this direction, I don't know. There's no in-principle way of telling whether this is a vertically polarized photon or a horizontally polarized. If it was emitted here, I know this guy is horizontal because that's the only phase matching I can get. And if the guy is emitted over here, I know it's vertical. But if it's emitted where this degenerate guy is, where those two things, I can't tell. There's nothing that tells me whether that photon is horizontal or vertical. The same thing is here. Yeah.
So is the twin of one of those points the other point? 'Cause
Yeah.
That's the only way that would make sense.
Well, there are, so there are, 4 processes here, right? But there are 2, if I take this, there's a twin, it's a twin, there's a twin, and then there are 2 twins in the other guys. There's 4 possible combinations. And particularly if I put my apertures here, then the state that I produce, there's no information about which polarization state those photons are. If I trace over the polarization of, if I trace over the momentum of the photons, it's fine. There's nothing, the momentum is not entangled with the position. So the state that I get out of this state is a polarization entangled state. And this is a big deal. You might recognize, or maybe not because it's such a crappy picture, this colors a thing. This was our icon of our web page for a long time. And if you Google quantum optics, this is what comes up because it's the coolest picture ever. What you end up with is if this is mode 1 and this is mode 2, those are the k vectors, is that the state of the system is equal to h1 v2 e to the I alpha 8 v2 h1. And that phase here depends on the crystal. And it's controllable. So in principle, you can make different phases of superpositions of these states. The point, again, is that because I cannot tell the polarization from the momentum, because the momentum of the photons is not correlated with this polarization, I can just trace over the momentum, and what's left is a polarization entangled state. The first experiment that was done by Schianelli in the University of Maryland, I believe, was a type 2 phase matching, but they didn't do this fancy trick of picking out the right momentum, orienting the crystal just right so that it did that. And they didn't get a highly entangled state because when you traced out the momentum, if you didn't measure the momentum had information about the polarization. And so it ended up mixing, creating a mixed state as opposed to a pure polarization. So all of the most sigma of violations of Bell's inequalities are all done with this kind of entangled. Now, not quite. Well, maybe I'll say just briefly here. So all these photons here were, say, H-polarized. So it has no polarization entanglement. If you take 2 different crystals, put them back to back, one that creates all H-polarized photons, and the other one that creates all V-polarized photons. But if the crystals are thin, so you don't know which crystal the photon was born in, then you get a superposition of H and V. And the whole, you don't just get these 2 points that overlap, you get the whole thing overlap. And that's called hyperentanglement, and we'll finish that next time. So that's the scoop. This is just a superposition. I mean, if I take an electron and, you do the famous Davidson-Gerwer double slit experiment, you put an electron in a double slit, it can go one way or the other. There's no entanglement. This is about superpositions, right? Well, yeah, but so, we would write this state typically, say, okay, this state in this goes to a state, and let's say this is a 50-50 beam splitter, and let's say that the phases were set such that you have a superposition with a positive sign in between. Okay, so entanglement, I don't think so. However, we can look at this in a slightly different way. Let's suppose, I'll come back to the front board here. So let's suppose that I look at this in second quantized notation. Okay? And so we know, as we've discussed and studied before, I can think about this classical beam splitter transformation. Yeah?
So before the beam splitter, you have Ka, and after the beam splitter, you have Ka again.
That's right. You have some fraction that gets transmitted and some fraction gets reflected. And if it gets transmitted, it's in the same wave vector. So it's one photon. There's some probability, if I can think about this, I put a detector here, or I put a detector here, there's some, this is if you wanted to go back to the first quantized notation, this is one photon in the mode Ka, and this is one photon in the mode Kb. But the reason I didn't write it this way is this is quantum mechanics that you've learned. I want to make it more complicated. I say that I expect, where even in the infinite dimensional case, we can write down this mu is a different mu than the one we're just typical index that we're using. So we can, even in the infinite dimensional case, write down a Schmidt decomposition. Generally would go to infinity, but maybe there's only a finite number of non-zero Schmidt coefficients in this decomposition, and that would say there's a finite amount of entanglement. So really I should say, in the same way that we've done before, even though it's an infinite dimensional space, typically this would go up to some maximum index, and the Schmidt rank would tell me something about the entanglement in momentum, and the entropy of the Schmidt coefficients will tell me a quantitative measure. So we could do that, certainly. Okay, so those are fairly straightforward things. But let's consider the following, that may be a little less straightforward. Let's suppose we did the following brain dead thing. I take a photon, it's in some incoming mode. Let me just keep my notation straight here. I think it really matters, but okay. So let's call this mode A. And let's just say I put it on a beam splitter. Okay, so let's say I did this. This was a single photon. And there's a mode B, and there's a wave vector associated with that direction. There's a wave vector come out. Okay. Is that an entangled state? Well, sure doesn't look like it. I mean, this is from elementary quantum mechanics, we would say I have a superposition of plane waves. It's a superposition state. But what the heck are you throwing entanglement at that mean? So that's nothing to do with entanglement. It generally would be of the form let's see. Yeah, so this is for one of the photons. With some important amplitudes there, right? So this is the kind of the momentum space wave function of the photon, and we would say this is in that space if square normalizable. So So an arbitrary state of the system, and here, of course, there might be some polarization index, but, we're assuming in this case, if we're talking about the sort of motional degrees of freedom or the momentum degrees of freedom, we would say, so take all the photons to be polarized in the same direction to start. And then an arbitrary state of the joint two-photon system in this Hilbert space would be of the form well, we have two photons, and there's some two-photon wave function. And that would describe the arbitrary two states here, or a state with two photons in it, with arbitrary two-photon momentum. Now, the question of entanglement here is trickier because we don't have an obvious way to think about a Schmidt decomposition of a matrix. In this case, these are infinite dimensional Hilbert spaces. But, we could do the kind of taste test on this and just see what the entropy is of the marginal state. That'll tell us something about the entanglement. And more formally, in fact, we can, and we'll look at this at homework, to describe this particular Hilbert space associated with two photons. And traditionally, sort of my friend Paul Kwiat, and everyone uses this notation now when we talk about polarization. You got the horizontal and vertical as my two orthogonal states of polarization. Think about them as linear polarization. And this would be the standard basis for that space, right? And we would write a general state of these two photons in terms of some kind of arbitrary decomposition of this sort, where these now are representing the indices, whether it be H or V. And as we have discussed in recent lectures, the degree of entanglement is related to the Schmidt decomposition. So that's a pretty straightforward thing to think about, right? Now, another way we might think about, instead of thinking about the spin degrees of freedom of the photon, we can think about the orbital degrees, as you like, or the motional degrees of freedom of the photon, all right? So another thing we might think about is, we'll think about two photons, and we'll talk about what is often termed momentum entanglement. And, well, it's a slightly more complex description of the system. We would say, in that case, our Hilbert space of interest would be representing, now we have infinite dimensional Hilbert spaces. We might say they're the Hilbert spaces associated with square normalizable functions, maybe in three-dimensional space, if our photons can propagate in three-dimensional space. So we have if we have some state, say, that is in one of these Hilbert spaces, we've been talking about in the last few lectures is the general theory of entanglement, right? And we learned a few different of the foundational points associated with that. What I want to talk about today, and we'll talk about in the next few lectures, is the realization of entanglement in quantum optics. And in particular, what I'm interested in discussing is entanglement in the quantized electromagnetic field. Now, this is actually quite an involved subject. It's not as straightforward as you might initially imagine, because as we discussed last lecture in their little makeup yesterday, entanglement is kind of in the eye of the beholder to some degree. It really depends on what are the subsystems that you're looking at, and how are you dividing, what are the degrees of freedom that you're actually trying to measure. Okay? So there are different ways we can think about the electromagnetic field, different kinds of degrees of freedom that we might think about entangling. The sort of most straightforward thing that you might think about is to think about two photons. And we might talk about polarization entanglement. So there we have, those are our degrees of freedom are associated with the spins of the photons, their polarization. And that's a pretty straightforward kind of thing that we know how to describe quite well. We have our Hilbert space associated with those degrees of freedom. They're kind of isomorphic to two spin 1/2 particles when we write our Hilbert space in terms of that kind of tensor product. And we might say, well, okay, we have some kind of standard basis